Good morning, everybody. Can you hear me okay? Okay. My name is Noble Nkwocha, and my collaborators on this study are Dr. Sang, Andrew Sang, from University of Mississippi. Uh, Dr. Liu is not here, and we compliment to our associate director who actually originated this study from the beginning. Marcus, please. I don't know if Marcus is here. The title of our presentation to you this morning, analysis of the effects of automatic, automatically generated code on the independent verification, validation of safety and mission critical software. Today, automatic code generation is both an emerging development practice and also an emerging development trend. Many of the efforts in in model-based software engineering, in which automated automatic code generation is most prevalent, aim at taking humans and the errors humans engender out of the software development process. Now, the emerging practice promises several things, one of which is a higher software quality. Higher software quality on the basis of eliminating and the errors that humans engender into the process of software development, especially in mission critical software. One key question that we ask is, do these promises hold? The promises hold to what degree or to what level do these promises hold? Well, the answer is we don't know. We don't know because the facts are that there are no empirical evidence in the form of studies of the effects of automatic generation on the verification and validation of software, embedded software in general, but especially on safety and mission for critical software. Now, here at NASA IV&V, there's a question on whether or not there are effects to IV&V analysis of the software if that software is generated from models. And the evidence we have, observational, it might be that our observational data suggests that there are actually effects to IV&V analysis on software. That software is automatically generated. In our investigation recently, I found three very important facts. In our study, we found three facts that we consider very, very important. The first of these facts is that several, rather than fewer, IV&V projects actually had automatically generated code. This fact was important because of the surprise. We went into doing this investigation, went in with the premise that far fewer of the have automatically generated code. The surprise was that several of them, in contrast to our expectation, actually did have automatically generated code. Now, I'll qualify to say that the level of automation or the level of auto-generated code used in the different projects varied, but we want to see that a little later. Now, the other aspect, the importance of this observation was that it indicated to us a trend that is going to continue. It is not going to abate. More and more safety critical mission software going to be generated automatically from models. Now, the second fact that we found was that there was a common theme that ran across all of projects that had automatic code that would. That common theme was the question of what area or what aspect of the automatically generated code IV&V analysis would focus on. And for the time constraint, the focus of our presentation to you this morning is going to be based on this second finding, which is the common theme that we say run across all of those projects. Now, the third important part, and actually consider this the most crucial, was the observation that the automatically generated code had higher slot counts than equivalently handwritten code. This is very important, and as much as we're not going to spend much time on this finding in our presentation today, but it is very considered one of the most crucial find. We consider one of the most crucial because from a software point of view, when we estimate the execution time of any task, of any thread in real time, especially in environments where the deadlines are rigid. We have hard deadlines for tasks, then the execution time of any task, of any thread is very crucial. And from an IT perspective, one of the things we'll look at is in hard deadline environments, we ask whether or not the tasks or the threads in that particular time environment are able to meet their deadline, their required deadlines. And so this is that's why the third fact that we found is considered almost most crucial of all the three facts that we saw. Okay, now in our investigation of the second fact, which was the question of what area of the auto-generated focus ought to be, led us to look at the question of how current IV&V methods treat automatic code. And what we found was that in every one of these projects, how current IV&V methods treated automatic code followed the automatic code generation flow. And this flow is depicted here. It essentially forms a contiguous three-phase process where the input models are developed and generated and then fed into the automatic code generator, which then spits out the result of the generation process, which is the software itself. And as we're going to see a little later in our presentation, the result of the resulting code falls into two categories: partially generated code and fully generated code. But suffice it to say that the importance of how IV&V methods treat automatic code follows the flow depicted in this diagram. Now, the second diagram we'll show you here. Actually, it supplements the first one. Both of them follow the same pattern. But this particular pattern was one of the examples we found was a little bit of a deviation of the first flow. In the case that the input to the code generator was not just modeled, but actually came out of requirements. Okay. Now, this is the focus of our presentation to you today. We limit our focus to this second to a second finding, the common theme that we found that ran across the projects, IV&V projects that we looked at. It was the key question, like we said, of given the three phases of the auto-cogeneration process, we have artifacts, we have IV&V artifacts or software artifacts that come out of each and every one of these phases. Now, it is not possible. It is for many reasons, known and unknown. One of which is it is costly prohibitive to do analysis, IV&V analysis, or V&V analysis for that matter, on all aspects of any software, including auto-generated code. So the question then is, where or what phases of, or where should the focus of IV&V analysis be? Should we focus it on analyze the input to the code generation, to the auto code generation? How about the generator itself? Besides that, the output, how about the output, the resulting code, which is traditionally where the focus of IV&V or general V&V relies on. The superfluous to that are the other aspect of it. How about IV&V, all of the different phases of the automatically generated code? And like we said earlier, it's almost not realistic to be able to do IV&V on all aspects of that phase. So somehow there has to be a way to determine where most of the focus of IV&V or even general V&V of the automatically generated code should be. Okay. Looking at the input models for doing IV&V on that aspect on that phase of the automatically generated code. Okay. What we found was that in general, most of the input models they came out of models depending on the tool that was used. In MATLAB, on the same link here, had MATLAB models, and Rhapsody, and we had UML models, and we had XML models, we had all different models. And in some cases, actually, we had inbuilt in-house models that were used as input to the code generator. Now, there are benefits to looking at the artifacts, the software artifacts from each one of the three phases. That we stress the major weaknesses that we found. The reason why we stress on these major weaknesses is that most of the benefits are already known benefits, and we didn't actually find anything crucial, important to report. Now, I'm doing analysis on the input phase, on the input models to the automatic code generation. One of the benefits that come out of it come from standard model-based software engineering. And as we know, anytime we work with models, one of the best results or best benefits of that is the cost. The cost is a lot lower than doing IV&V on the real system. But also we know that also comes with some costs. Okay, a model. Every time we run a model, it brings in it brings up issues like risks, and the fact that the model is not the real system still puts a limit to how much IV&V or V&V we can do on that. But some of the key weaknesses we found in doing IV&V on the input models were that the focus on the models, as we saw, were mainly on what was modeled, on the inputs that were modeled. The models were not were not all encompassing essentially. In essence, if a focus, if the input or if the input model did not, if a scenario or a use case was not represented in the model, that use case was not was not was not considered, was not issues from that use case were not visible. Now, also found that there, a lot of abnormal behaviors were not defined in the input in the input models. One of the things we're going to see when we look at doing IV&V and the output of the autocode generation process is that one of the abnormal behaviors is the fact that we found out that it was common that a lot of open files, there were a lot of memory leakages essentially, and a lot of resources were not managed very well. One of which is there was a lack of enforcement of assuring that every open file, every file that was opened had a matching clause. And as we see, and what we found out that one of the reasons why that was the case was because it was impossible for the during the modeling to know when an object was, when the life expectancy of an object was, when it was over, in order to close that particular file descriptor appropriately. Now, the other major weakness that we found was that the derived and implicit requirements are more likely to be missed if the scenario of the use case was not that obvious. It was not modeled in the input model. And finally, the other thing we found was that presently the techniques we have for IV&V for analyzing software models are not very prevalent. Typically, we'll work on artifacts and documents from requirements documents to CANAPS documents, and all through to the test plan and test design. But that's quite different when we're doing IV&V or V&V on automatically generate code, especially on the input models. Okay. Now, if we're not doing IV&V, if we're not IV&V in the input model, then the next question is, should we do it on the code generator itself? Now, exploring the question of whether we should do IV&V on the code generator itself led us into three sub questions. The first was, whether or not we can trust the generator. Okay. Is the code generator is it an off-the-shelf product? Has IV&V already been done on it, or can if IV&V is not done on it, or if we don't have any public information on what type of V&V or IV&V have been done on it, if we had a certification, if we had a certification on of the generator, could that be substituted for IV&V? Okay, these were some of the questions that we ended up exploring as we progress in our study. Now, in the context of IV&V, what we found was that the majority of the code generators fell under the category of code software. Admittedly, there were a couple of examples where the code generator were in-house tools. They were not exactly commercially available, but nevertheless, there were common weaknesses that we found in exploring or doing IV&V on the code generation. Okay. One of the key findings we had here was that just like any of the other code software, IV&V or any V&V organization will have to rely on the V&V that's done presumably done by the manufacturer, by the vendor of that particular tool. But more so, we know that in safety and mission critical software, one of the key no-nos is having dormant code, code that's not reachable, that's not exercised in the system software. Now, this is very common in auto-generated code. The fact is that any tool, any CAD software, uh, you know, in any CAD software environment, there'll always be features of that tool that are not exercised in any one application of it or implementation of it. The result of that is that there is always dormant code that is not exercised, that IV&V will not be able to exercise. Not just IV&V, any V&V operation in general will not be able to exercise. And so we think that is that is an issue. If we had to certify, a software, we cannot. It'd be impossible to certify an auto-generated code on the basis of the auto code generator, because there will always be dormant code, and if we have dormant code, we cannot justify the certification of that software. Okay, and in the final on this particular looking at focusing on doing IV&V on the code generator. Okay, the V&V techniques available to us on limits up to the black box approach. We don't have insight. We don't have insight into the inner workings of the tool. So there'll be no way to exercise the tool through the limits. Now the nominal and off nominal scenarios would be almost impossible to exercise. And in the case from an IV&V perspective, that is a major limitation. Systems that this embedded software run, we check the correctness or the validity of this CAD software for what they are. We do not IV&V the GCC compiler. We do not IV&V any of the compilers that the software runs on. Although somehow in web practice, you have to somehow qualify the compiler as during your qualification, the software developer's qualification procedure. But in general, we take for granted or we assume the correctness of this CAD software. The same thing is exactly the case with doing IV&V analysis on the autocode generator itself. Okay. And the third phase of the automatic code generation flow is the output. This is the code itself. Now, what we found also is that the resulting software from the auto code generation process fell into two categories. Those that were fully automatically generated. In this particular instances, very little modification or cleanup were required to complete the software after the code generation process. And the second category of this code software, the partially auto-generated code. And partially automatically generated code, all found that several of the projects use automatic code generation or use the tool, the generator, to generate skeletons and stubs of the software, and then manually fill in the rest of the and the rest of the code. For the target language, programming languages, in our study, we found out that there were no Java code, there were no Java automatically generated code. That is not to say that there are no automatically generated code in Java, but in the project that we looked at, we didn't find any Java code in there. The code that we found were mostly C, C++, and Ada. But it was more of C code instead of C and C++ and Ada. But absolutely no, there were no Java auto-generate code. Now, among the general issues we saw looking at doing IV&V or focusing IV&V on the output code, was one of the most common ones was lack of code documentation. Well, we know that in software, code documentation, there's more to code documentation than comments. We have comments in the code, but a good code documentation, if a handwritten code documentation, or if you teach software engineering and computer programming class, one of the things you teach in your introductory computer programming class is good coding. You teach your students that it doesn't suffice to just add comments. As much as it is very important to comment your code, but other types of documentation, including good identifier names that had meanings that the reader could make sense out of. Things that are features or things that improved or that enhanced readability and the ability of somebody else reading your code being able to understand what you're doing, and staying away from identifier codes like I, J, and K. Instead of using I, J, and K, use things that make sense. But what we found is that in the code, in the automatically generated code, the lack of documentation, good documentation in this sense, was a very big issue. The result of that, or the consequence of that, is the comprehensibility of these codes were higher, were worse than the equivalently handwritten code. Now, the other common issue we found was the issue of resource leaks. Resource leaks were common among the automatically generated code. And again, I think I tried to make this point earlier. Intuition told us that one of the reasons was that it was difficult knowing tracking the life expectancy of an object in the automatically generated code. Manually written, we don't delete an object until that object is no more needed. Well, we don't know when the code is automatically generated. We don't know exactly when that object is not needed, and because of that, there's no matching deletion of an object once the object is no longer in existence. And the files, for example, the other resource leak was the absence of assuring that every open statement, every file open had a matching close statement to close the file. And we think that the reason that was the case was because, again, it was hard, in automatically generated code to be able to remember when a resource and a file that's opened needs to be closed. In handwritten code, it's actually easier. Every time you open a file, you always know, you keep in the back of your mind that one of the key things that has to be done is to make sure that that file is closed. And so that was exactly the same case here. We're looking at doing IV&V on the resulting code from the autocode generation process. Garbage collection was not strongly enforced either. And all of these issues seem to have the same common theme. They were not the theme we found here were, again, in automatic code generation, in automatically generated code, it was hard for the tool, even for the models from which the code were generated, it was hard for them to tell when an object or when a resource is no longer needed to clean it up appropriately. And besides that, there was also the case of, like we said a little earlier, the majority of the projects we looked at, the programming language was C instead of C++. So garbage collection, there's no automatic garbage collection. So the garbage collection had to have been built into the models for it to have been implemented. In addition to that, we also saw some issues that were unique to, that were unique to the target processor. This particular issue is something that we think we need to explore a little further. Okay. Now, we looked at doing IV&V analysis on the different phases, the input model, the code generator, and the output code. In addition to that, one of the general things we saw were that, and some of the general things we saw were that, the focus of the auto code generation did not encompass all aspects of the software. It seemed to, the focus seemed to be in specialized domains like guidance, navigation, and control domains instead of the entire mission of flight software. And from an IV&V perspective, what we also found was that some of the projects, some of the auto-generated code have fewer errors than hand-coded errors, and we add this to the errors, to the compiler being more effective, or the generator being more effective, more efficient than the human. And in our own particular context, we found out that the static code and the results of static code analysis and automatically generated code found far less severe issues. As it says, severity 1 to 3 issues, which in our context, from NASA IV&V context, severity 1 is the highest severity error. So there are far fewer of these that were found as compared to the handwritten equivalent. Okay. In one of the projects we looked at, one of the tools, the result of the generic code was just very bad, and a decision was made not to do IV&V analysis on it. Okay. Now, one of the questions that my supervisor then, our associate director asked was whether or not the common issue we saw could be remedied by having a better input model. And I looked at it, and my response was perhaps yes, perhaps no. What we found out was that remedying, the remedy to the issues we saw applied. Some of them applied more in one phase than they applied in other phases. Some of them were better remedied. Some of the issues we found were better remedied in the output code than they were remedying them or trying to find solutions to them during the start of the modern phase. Now, we recommend adding IV&V method that address these weaknesses, and one of them then we recommend doing dynamic analysis on them, and then with rules of engagement for auto-generated, doing IV&V on automatically generated code. Our ICAD, the NASA IV&V project execution plan, straddles exactly the way we think the auto code generation process should follow. And finally, for future research, we recommend doing mutation testing analysis. Mutation testing analysis where the key components of the auto-generated code are mutated, and then the effects of disease, the effects on mutating those key components observed and recorded. Questions, please? Yes.
Please step up to the microphones. A question in the room. And while you're approaching the microphone, I'll share a comment that was stated online. Go ahead and walk up to the microphone while I share this. James Healy says that on SGSS, they also found a strange code logic like always true condition statements.
Okay. Thank you.
Any of the three microphones you can ask questions of. Make it quick. We got a couple minutes.
Your presentation hit home because we are on the ISS project going to be looking at the large amounts of autocode we get from Matrix X, and we're not too sure how to go about doing that, but your presentation gave us some ideas. I had a question on the things you typically have in autocode that are hard to find, like memory management, memory leaks, the garbage collection, and the mutex and resource management. Do you think static code analysis tools will find most of those problems, or will you miss most of them? What's your experience with that?
Okay. What we saw, what we saw in our study that the essence of the resource lakes, came from the input model to the autocode generation, and the reason we think that that it came from the model is that during the modeling was almost impossible for the input model to know when a resource lake, when a mutual exclusion of mutex, for example, when it was time to release a mutex, knowing that once you acquire a mutex, that there had to be a match and release to avoid deadlock, right? Mm-hmm. And to avoid one thread or one task hanging. So it was almost impossible to add that into the modeling. Take the file, the case with not always enforcing a closed statement with every open statement in the code. It was also a case that it was impossible for them to be able to determine when the life expectancy of that particular object, of a object, for example, had expired, so that they could close it appropriately.
So by running a static code analysis tool, will I pick up these problems, or will it be hard to do that?
No, running code analysis, static code analysis will actually. And what we showed, or what we observed, was that static code analysis found fewer errors with automatically code generated, fewer high severity errors with automatically code generation than the equivalent in handwritten code. But what I'd like to stress to you is one of the key things, one of the key findings we had was, especially with Matrix X, is a higher slot count of the resulting code compared to the equivalent in handwritten code. And the reason why we consider that more crucial, most crucial of the three findings so far, is that they affect the execution time of every task, every thread in the application. And you know that one of the worst things you want to do is to have a deadline or have a task that's not able to meet its deadline. And the ability of a task or a thread to meet its deadline depends on that task's execution time.
Okay. Well, you've given me lots to think about. I will contact you for any further questions I have.